as you said, I spent quite a lot of time in Edinburgh, and so it's just wonderful to be part of this of the festival that I've visited many times in the past. And also, this work that I primarily did while I was at the National Museum of Scotland for the past 5 years.
Sorry, David, are you muted? And that was my fault.
Right. Shall I restart?
Start again, sorry. We
All
got
right.
you just the beginning of your talk, sorry.
Yeah, sounds good. So as Emily said, I've been in Edinburgh for a few years, so it's wonderful to be able to share this work that I've done in Scotland with you here at the Scottish Festival of Geology. So I have a lot of people to thank, first of all. Many of my colleagues at the NMS, Nick Fraser, Stig Walsh, and colleagues at the University of Birmingham, so Richard Butler, NHM in London, Paul Barrett, University of Edinburgh, Steve Brusati, and here Virginia Tech, Sterling Nesbitt. And also our founders. So my postdoc was founded by the Royal Commission for the Exhibition of 1851. And I would also like to thank our friends at the Elgin Museum, which were really accommodating and helped a lot during this project. So everything I'm going to talk about this evening is the results of a lot of teamwork. So thank me, but also thank all these people here. Without whose help, this would have not been possible. So this is what briefly I'm going to talk about. Elgin reptiles, I promised. So what are they? Where did they live? When did they live? Why are so important? How have they been studied in the past? And why do we need to restudy them? And how can we do that? And then I'll spend the second part of my talk talking about a case study of one of these reptiles, which is called Scleromoculus. And I'll explain why that is important and what new things we learned using new technology. So what are the Elgin reptiles? So Elgin reptiles is a collective name that groups a series of Permian and Triassic fossils that were found that are found in sandstone deposit around the Elgin area in Moray. So here in there in Scotland. They are of historical and scientific importance because they were among the first faunas of this period to be fully described. And good news, you can see them around many collections. So there's a few specimens on exhibit in the National Museum of Scotland, both on the basement floor where there are some footprints, and also in the History of Scotland gallery, you have some specimens, both Permian and Triassic, I think. At the Natural History Museum in London, there are some specimens. And at the Elgin Museum, you got lots of them. Not only in the museum, but also if you visit around the quarries, there are informative panels about these specimens. And if you fancy these things, the collection of these institutions are full of these specimens. So where were we? So Scotland, the world was very different about 230 million years ago, and in the Triassic, and these also apply for the Permian. But here is a map of what the world looked like in the late Triassic. All continents, and as you see, were together in a supercontinent called Pangaea. Europe was mashed against North America, South America, Africa. The Atlantic Ocean had not started open yet, and the UK was around here, much closer to the equator, in between North America, Europe, and Greenland. So not only the geography was very different then, but also the climate. Being this area much closer to the equator and surrounded by land, the climate was very different. And in fact, most of the fossils that we find, at least in the Triassic deposits, were covered by deserts dunes. So what we call this type of rock sandstone, and it's in particular an Aeolian sandstone, so a sand that has been accumulated by the action of the wind. So something that you can see in a desert environment nowadays. This does not mean that there was no water around. In fact, just below the layers where these fossils are found, there's evidence that some water would flow. It's just that all these animals have been actually covered by advancing sand dunes. At least that's what we think about. Unfortunately, I cannot tell you much more about the environment around because we have very little evidence of plants, very little evidence of insect, if actually none of those. And all we are left is with some fossils. So a little bit more about the geology around the area. So we are in Moray, in the northeast part of Scotland here. We have different kind of formations of different age, from Devonian through Jurassic. And what we are going to focus today is the Permian sandstone, so both Hopman and Birkhead, which is in this orangey and reddish color, and also primarily on the Triassic fauna, which is in the green looking layers here. And all across these areas, there are several quarries. And that was part of the reason why we managed to find so many fossils. So these quarries have been used extensively since the 1800s, or even before probably, as building stones for quarrying out building stones, which means that there was a lot of action within this deposit, which allowed workers to uncover many fossils. If you look around Edinburgh, actually, many buildings are paved, if not and covered by sandstone from this area. One example is the National Museum of Scotland, which is covered by sandstone from, I believe, the Clashach quarry, but might be wrong. Anyway, all these quarries were wonderful because it allowed us to find many, many fossils. Nowadays, the situation is a little bit different because, as you can see from the photos behind, down here, B and C, now there's a heavy machinery which scrapes sandstone directly from the walls and reduce them directly to shard on the spot, which is a problem if you're a fossil. So a lot of this gravel is used for gardening, and so it's check your garden if you see any shard of these things. My colleague at the National Museum of Scotland managed to visit one of the quarries back in 2016, and they managed to find some bones across some layer. And as a consequence of that, and thank you also to the staff of the Elgin Museum, we talked to the workers of the area. So we told them how to recognize the fossils. So if anything comes out, they'll be able to point to us, as it happened actually not too recently. When in time are we? So these are brief a summary of the history of Earth, well, part of it. And Scotland has a super rich fossil record. I'm just going to point to very few things. It's not an exhaustive list, and keep following the festival to learn more about the stuff. So in the Pentlands, Dumfries and Galloway, you can find fossil from the Ordovician Silurian. You got trilobites, graptolites, sea scorpions, and stuff like that. In Fife, you can find wonderful Devonian and Carboniferous fossils, including plants. Further back closer to us in time, you may have heard news about dinosaurs, pterosaurs, footprints, early mammals, turtles, salamanders from the Isle of Skye. And right in the middle of those, there are two actually assemblages of fossil reptiles from the Elgin area. The Permian and the Triassic, which are, again, two different ones. One occurred in the Permian, probably late Permian, and one in the late Triassic. So why am I being so specific about this? Because in between those, there was a giant mass extinction. This means that these two ecosystems that were separated by about 20, if not more, million years occurred, one before the Permian-Triassic mass extinction and one after. And as I'll show you briefly later, these are completely different worlds. We do not have an absolute age of data available for the deposit, but based on similarities with other formations and other faunas around the world, we can say that the Permian was probably late Permian and the Triassic was probably late Triassic. So mention mass extinction, why are these important? This is a little bit of bias because I'm working on mass extinction right now, so please indulge me on that. Mass extinction play a fundamental role in shaping life on Earth. That's because on the short term, you can imagine that extinction reduce diversity of animals, pruning a lot of the branches of the family trees of animals. But on the longer term, these they empty ecological spaces for other animals to fill in. So potentially they create opportunities for different groups to flourish past the extinction. And the Permian mass extinction is a good example of this. So the Permian mass extinction occurred about 252 million years ago. And I don't want to be too specific about this, but separate two completely different worlds. About 96% of species, up to 70% of species of land vertebrates went extinct, which means that the faunas of the Permian that were dominated by animals called synapsid, so animal more closely related to mammals than to other reptiles, are very different from the faunas of the Triassic. And the effect of this extinction are visible still today because it is just at the beginning of the Triassic that modern fauna start evolving. What I mean by that? I mean that the very early ancestor of birds, crocodiles, turtles, lizards started, and crocodiles already said that. Anyway, they all start evolving after the Permian-Triassic mass extinction. And that's something I want to stress because the very early relatives of dinosaurs, pterosaurs, potentially turtles and crocodiles are all present in the Elgin fauna. So with the Permian, when we've just started working on these things, and we hope to expand this research in the future, the Permian was full of weird animals. We have on the top left here a dicynodont. This is the eye, this is the nose. So nose on the left, this animal had big tusks, probably a beak on the front. They were herbivores. There's nothing about those things that are similar to animal today's. And even weirder, perhaps, parasaurs that are actually more closely to reptiles. And this horned, very ornamented, weird thing. We have big horns on the back of the skull, big orbit there. The nose this time points on the right, and teeth that suggest that these animals were potentially herbivores. Not only we have this kind of animals, but we have a really diverse footprint assemblage. We have footprints of many size and different types, which suggests that the diversity of this fauna still have to be discovered. So keeping an eye on these rocks would be very important in now and in the future as well. And yeah, visit the Elgin Museum to see many more of these footprints and this animal in exhibit. But what I would like to focus more today is the Triassic fauna. And that's because I spent most of my past 4 years working on those. And because, as I said before, they are super important to understand the evolution of modern faunas. To underline again how diverse and how important these animals are, I'll just circle a few of them. This animal here look like a lizard. That's because it does look like a lizard. It's one of the earliest relatives of tuataras, which a group called rhynchocephalians. The only living member of this animal is of this group is tuatara nowadays and lives in New Zealand. These two weird-looking things are para-reptiles, so perhaps more closely related to the horned animal that I showed you before. We have what's going on? This thing. This is an herbivore archosaur. Again, started evolving after the Permian-Triassic mass extinction. It had a beak there. It's called a rhynchosaur. And then we have a series of archosaurs, which is a group of reptiles more closely related to birds than they are, and crocodile than they are to lizards. And it's this one, that one, and that one. And as you can see, there are 4 different kind of crocodile line archosaur that were very diverse. One is a carnivore of a large size. One is a small size carnivore. One is a herbivore, looking like an armadillo, so super odd. And then a middle-sized carnivore, which potentially stood on 2 feet on its legs, so very, very odd. To look on some more famous animals, we have Avemetatarsalia, which are the group of archosaurs that are more closely related to birds and dinosaurs than they are to crocodiles. And these things, you would think they are very similar to dinosaurs. That's because they probably were one of the very early relative of those, of dinosaurs. This animal is called Saltopus. And then you have these tiny things. This is Scleromochlus, and it was suggested to be closely related to pterosaurs. And that's the animal I'm going to talk extensively about in a little bit. So with this huge diversity, let's try to place these in the reptile family tree. Procolophonidae are closely related to, are outside, a little bit outside the modern reptiles, so in a group called the para-reptiles. So they place there. Brachyrhinodon, the lizard-looking thing, is one of the first early ancestor of lepidosaurs, so the groups that today contains tuatara, lizards, and snakes. Then we have Rhynchosaur, the weird-looking one with the beak. Saltopus, one of the early dinosaurs. Scleromochlus, potentially a pterosaur, question mark. And then a huge diversity of crocodile-like animals. So why do we need to study these animals? So because even if they've been studied extensively since the 1800s, they are still poorly understood. And the reason for that, you can see it in this specimen, is that the preservation is horrific. It's really horrible. You cannot see a bone in there. That's simply because there's no bone. What happened in most of these small-sized specimens is that the bones have been either dissolved chemically through fossilization or it has been removed manually. The bone, when present, is in crumbs, which means that you have crumbly material encased in a hard material, which is absolutely impossible and a nightmare to prepare. So what happened in the past is that people have, they knew that there were fossils within these rocks, and they started paying attention on holes they could see on the surface. Once they saw a hole, they would just crack the rock in half, hoping that it would split across the skeleton. And if there were cavities to infill, they would fill them with wax or resins or other materials. And then once those materials were set, they were peeling those away and they were left with this sort of material to study. So you can study essentially the molds of the bones left on these sort of materials. There are many problems with this. This was necessary in the past, but this technique are destructive because you have to crack apart a block. But not only, when you peel away these resins, they take away part of sandstone, which is a problem. And that's a problem because every time you want to restudy these fossils or you want to make a new peel for different institutions or different researchers, you are taking away details sequentially. Other issue with this, so this causes a loss of detail. Other issue with this is that you can do one surface at the time. So imagine you crack a rock in half, you have two halves, you have to mold one first and then the other first, which is a problem because if you have a bone that is sticking in between those, between two different slabs, then you are studying half of the bone at a time. So, and this is what happened with this sort of material. The last problem, which is potentially the most problematic, is that resins and wax do not reach all the cavities. Either because when you crack the slab, you did not expose some of the cavities, or because the cavities are too small. Either way, you're just having an incomplete picture of what the fossil looked like. And actually, this is the most problematic thing of all. These peels are soon becoming unusable. So I've seen many of those in a different institution. They are crumbling. When you were lucky, some are becoming gooey, so very weird consistency, sort of gelatin-like, hold together by a crumbly surface, really odd. But the bottom line is that we have fossils that we've broken. We cannot do more of the more cavities, like more peels like this, and soon we are not going to be able to use those. So this was the main reason to do this project. And a solution for that is using computed tomography. Computed tomography is a technique that derived from X-rays, which has been used in paleontology for a long time. It has become a common technique to use nowadays, and it has multiple advantages. So first of all, how it works. So when you go to the hospital because you hurt your hand, you have an X-ray to it. This is a 2D image. Now imagine that you do an X-ray at every different angle of your hand. And with a computer, you can put these different angles together and create a 3D model of your actual hand. With this 3D generated data set, you can manipulate them, you can turn them around. I'll show you in a bit. You can 3D print them, and you can create digital and durable substitute that will last forever, theoretically. These techniques are non-destructive, so specimens that have not been prepared, you can scan them without having to break them. And you can do that also for specimens that are difficult or impossible to prepare. The last advantage that one of the other advantages that you have is that you can see hidden structure or hidden cavities, like a brain case cavity that you would otherwise not be able to look at. So let's see a few examples of this. This one is one of the very few specimens that have not been prepared that I've seen. You can see the holes there. I circled them. If we cut them through digitally, this is what we see. The gray is rock, and the blacks are also what the fossils look like here. So what I literally do for a long time is every slice of this rock, I circle around the cavities, color them in very patiently with different algorithm. Do that for all of them. Different color if you feel fancy. And then at the end of it, that's what you come out. You can reconstruct an entire skeleton that you had no idea was this complete inside that rock, and there was no way you would be able to prepare this specimen before. So this animal, for example, also has some part of its last meal, probably. Still don't know what that is. I know what the animal is, and it's one of those survivor of the extinction, a little lizard-looking parareptile called the leptopleuron. Other examples that you can see bones that cannot see in the surface. So these several blocks that I put together from BGS, you can remove the rock, and you have not one, but at least two, if not three different animal skeletons in there. This one is the head of one of the leptopleuron as before, while everything else probably belong on an animal called Herpetosuchus. And if you want to read more about that, we published this. Another example here, if we look at the early ancestor of lizards, of Tuataras, Brachyrhinodon, I took a slice through the CT scans, and you can see different parts colored here. So the blue parts are pieces of bones, of the original bones. And I highlighted in red the part that the peels were not able to access. So we know nothing about the red part before we CT scanned this area. And the problem in this case was that the resins were not able to access to that cavity because of these leftover bones there. At the end of the day, we reconstructed this, and in gray, you can see what was originally known, and in red, you can see what was not known. And I can actually try to show you how this works in a real case. So, spoiler, that is. So this is the rock where that skull belongs. There's a crack here. I put back together with rubber bands to have both half put together. Now, if you remove the rocks, you can see now the skull. This is in real life, it's about 2 centimeters long. So already the advantage to be able to increase the zoom on this is phenomenal. And then I can add the extra detail that we found through CT scanning. So you can see minuscule details. This part of the throat bone, this must be few millimeter long and less than a millimeter wide. So if you look at this part, this long part there was not that known before, and now we know it's there. So a lot of to be gained to do this sort of exercise. Where we had most gains, though, is Scleromoculus taylori. And this animal has baffled paleontologists for a long, long time. And I'm going to explain you a little bit why. So this animal is absolutely tiny. You can see that fits in the hand of one of our colleagues. I also have a beautiful reconstruction of one of my colleagues at the NMS. So thank you, Sarah. This was useful. And I can overlap there. I'll show a smaller reconstruction. So these triangular bits are the head. There are actually two skeletons in this slab. And this animal has been known since the early 1900s. It's tiny, as said, with it in your hand. It's been studied from casts. But because of all the information that we were missing, we had a very weird picture of an animal that didn't fit really anywhere in the reptile family tree that we thought of. So this animal has been described as having a flat head, sort of like a frog, very long, a short neck, very long legs, but short arms, and a super short tail. and also a shallow rib cage, again, like a frog. So imagine one of the images of this animal was something that was sprawling in a position, well, walking around like a lizard or hopping around like a frog. I'll tell you more about that later. But all this uncertainty about the anatomy of the animal creates uncertainty on where in the reptile family tree this fit. It has been thought to be close to the origin of pterosaurs, but also we have many questions about its biology that we do not know clearly. So how did he walk around? What did he feed on? And so on. So just to underline how little we know about Scleromoculus, these are just a few of the positions in the reptile family tree where it has been supposed to be. It is supposed to be one of the early relatives of crocodiles. So in the Pseudosuchia, in the crocodile line, Archosaur lineage. It has been suggested to be closely related to dinosaurs. It has been suggested to be an early ancestor of pterosaurs, as this illustration shows you. So in this case, this would be the idea that we had of Scleromoculus, some people had of Scleromoculus about. So directly on the line that would evolve into pterosaurs. Some other researchers suggested that no, that's too derived. Scleromoculus was actually one of the in one of the early branches of reptiles post the extinction. So somewhere around here. So what we did is what I showed you before. So here we took the two slabs, put them together, scanned them. Then we were able to recreate the peels, but this time our 3D model of the peel, so you could see the front and the back of the same slab. So this allows us to isolate individual bones that were previously split into different peels, but also with the CT scans in blue, you see all the extra details that we were able to find out. There's an entire arm there. Let's see, there's part of the foot there in yellow, all the ribs, and these are all part that the CT scan were not, well, that the peels, the original peels were not able to access. So a lot to work on. And we did that for all the 6 available specimens of this. And again, you can see in red how much does our understanding of this animal has changed. So for instance, here we have a tail, super long, at least double the length of what we thought before. As I show you how long the ribs are. So remember I told you that the peels only capture a little part of the ribs. So it was thought that Scleromoculus had very short ribs, as you can see in this representation there. And then you have extra details of many other parts. Putting all this together, Matt Humpage was able to create this absolutely wonderful reconstruction. And again, I can show you a little bit more of this. This is the spoiler I told you before. So Matt was able to recreate this absolute beautiful reconstruction of a 3D skeleton. So you can see all the amazing details that were all based on the CT scans that we have. So 5 centimeters here, so super tiny. We have a better understanding of what the skull looked like and all the limbs and et cetera, et cetera. And soon, hopefully, you'll be able to navigate this animal, this representation, because a paper should be coming out soon, hopefully. From current slide. So what did we learn using CT scan on Scleromoculus? We learned, as I mentioned before, that the tail was not short, but was super long. The torso was quite deep. Both limbs, both the leg and the forelimb were rather long, which changed our understanding of what this animal moved around. And so the notion that this animal had a flat head and a flat torso and was a sprawling animal, we found that unconvincing overall for several reasons. But putting all this together and testing numerically all these different characteristics with other reptiles, we were able to understand where Scleromochlus actually fit in the reptile family tree. Oh, I forgot the foot, my favorite part here. So we have a lot of more information about the foot, and this is a claw, which is about 1 millimeter long. So this gives you an idea on how beautiful the detail of these scans is. And overall, then we have now evidence that Scleromochlus was not a direct ancestor of pterosaurs, but closely related. So probably part of a group called Lagerpetid. And Lagerpetid were a group of small, medium to small sized reptiles that were thought to be closely related to dinosaurs. But now that we thought we are the closest relative to pterosaurs. Briefly, I don't think I have too much time, but I'll go a bit faster. How did this animal move? It has been suggested to be a runner, to go around sprawling like a frog or hopping like a frog, or going around like a little kangaroo as well. So our review showed that this was probably not the case. This animal was probably not standing on all four because that very small hand, small shoulder girdle, it was probably not going around jumping because it were not reinforced, so just very small. And so we tried to test a bit more numerically the stance and also the running capability of this animal. So we measured how long the arm were compared to the legs, essentially. And you can see here that in crocodiles, the arm is pretty much as long as the legs, which means that the animal was probably standing on all four. On the other hand, if you look at some dinosaurs, their arms are much shorter than their legs, which means that they were probably standing on two legs. And Scleromochlus, unfortunately, cluster in an area where of animals that are being suggested to do a little bit of both. So completely not very useful. So we tried a little bit further and we looked at how long the torso, the rib cage essentially of this animal was compared to the legs. And again, these equations are related to the position of the center of mass. If the hind limb, if the leg is much longer than the trunk, then that brings the center of mass back, which suggests that the animal was standing on two legs. And that seems to be the case with these metrics. Finally, was it a good runner? Yes, it was. So we can say that by looking at the length of the foot compared to the length of the thigh bone. And in modern animals, it is a predictor of maximum speed that an animal can have. And Scleromochlus, there's little doubt that was clustering in an area of high cursorial animals, which means the animals that were very good at running. Some takeaway points. Scotland has a super rich fossil record that spans millions and millions of years, and you should go explore it, both in museums and outside. If you live in Edinburgh, you have the Pensel next door, you can find trilobites there, you can find brachiopods, so do it, it's fun. The Elgin reptile lived in two separate periods of time, Permian and Triassic, and tells a story about the war before and after the most severe mass extinction that occurred on land. Finally, well, not finally, the Triassic reptiles are a window on the early evolution of modern faunas that we were able to explore thanks to new technology. The most important feature of this new work is that, to me, provides durable and easily shareable data for researchers around the globe. And of course, it gives us more data, but we have data we can work on forever now. Scleromorphus, I already told you about it. It's, from what we know, it's probably a close relative, but not a direct ancestor of pterosaurs, and probably stood on, was probably not a hopper like a frog, was not probably going around sprawling, and probably was a good runner, at least capable of standing on two legs. Some work in progress here. A little shout out to some of my colleagues. So Emily Keeble at Virginia Tech is working on one of these herbivore crocodile relatives and looking at their teeth and how their shape can tell us about the evolution of this animal. And then Hedy George at the University of Edinburgh has just finished is finishing, I hope, his project on Gordonia, on Basinodont, and is investigating actually the brain cavity of this animal. So it's one of the first projects that we've done on the Permian-Triassic, on Permian fossils, and I hope that we will be able to do much more of this in the future. Many more, again, work for years. So yeah, references, thank you very much. If you have any questions, I'll be happy to answer them or try to.